Chem 1A, this is Chapter 8, Lecture Video 6, and we're going to be discussing the last two quantum numbers that we haven't covered yet, which are the magnetic quantum number and the spin quantum number. A little bit of review from the last lecture video. The principal quantum number, symbol N, is related to the energy level. And the other quantum number we covered, which is the angular momentum quantum number, lowercase l symbol, is the type of orbital we have present. Now, each subshell, or L value, angular momentum quantum number, can be separated into different orientations in space of the same type of orbital. For instance, if we think about p orbitals have like a dumbbell-like shape like that. I'm a horrible artist, but it's good enough. Now, if we think about this, it can be up-down, it can be left-right, or it actually could be out in front. So this is like coming out at you. This is going back away from you. Think of it like as a flat and coming towards you and out back from you. There are three orientations p orbitals can take, and I have a digital image that's going to do this better in a second. ML values, therefore, are dictated by the L value that we have for the system, right? So if we're talking about a p orbital, then we have very specific ML, or magnetic quantum numbers, for a p orbital. We have very specific ones for a d orbital, an f orbital, an s orbital. Our ML values always range from L to negative L on an increment of 1, right? So for instance, if we have a p orbital, L value of 1, the ML values therefore would be 1, because L, to negative L, okay, then 0 and negative 1. If we did an L value of 2, right, d orbital now, the possible MLs are going to be 2, this is the bullet point, 2, 1, 0, negative 1, and negative 2. Now, the crazy thing about this is it not only tells us that there are different orientations in space, it actually tells us how many orbitals are present in our atom of that type at that energy level. For instance, if I have d orbitals at energy level, let's say 6 or 5, I have 5 d orbitals at energy level 5 because I have 5 magnetic quantum numbers. Each one of these is a different atomic orbital for the d orbitals. There are always 5 d orbitals present at every energy level you have a d orbital. This is true of all the orbitals. So p orbitals, L value of 1, if you think about it, have 3 ML values, 1, 0, and negative 1. That means there are 3 p orbitals present at every energy level we have p orbitals. And they take on 3 different orientations in space. You can see them here. All right, so if you have any questions, let me know about this. We're going to talk about the next quantum number in a second. Number is pretty straightforward. Electrons can have different spins. Now, these spins that we're talking about aren't like literally spinning like a top type scenario. It's actually the magnetic spin. Or in other words, the magnetic field is spinning. If you've taken like the second semester of college level physics, you would have learned that when you have an electric field moving in a direction, around that electric field, a magnetic field is spinning. Now, it can be spinning clockwise or counterclockwise, depending on which direction well, actually, I drew this wrong. Should have been going the other way. And this one should be going the way I drew earlier. And if you've ever taken this, you would have known this as like the right-hand rule. But anyways, when an electron moves through space, it creates an electric field, which then generates a magnetic field that spins around it. All that's really neat. I need you to just know that there are 2 different MS values. It's either -1/2 or +1/2. And these, again, are associated with the different magnetic field spins that our electron has as it moves upwards, or it moves in a direction. Now, we can't actually tell which of these is the one we have. So technically, if you're asked what the spin quantum number is, as long as you pick one, most of the time, you really could pick either one and you'd be correct. There are certain questions where it might have to be one of the values based on context, and we'll go over one like that as well. Okay. So if you have any questions, just let me know. Let's continue on. So, Wolfgang Pauli is kind of like a famous physicist in this realm, and I just love his first name. It's such a cool first name. Nonetheless, famous chemist slash physicist, and he stated that he found that no more than 2 electrons can occupy the same orbital. And if there are 2 electrons in the same orbital, they must have opposite spins. Now, this is where it might happen where you actually have to pick a very specific MS value, and we'll talk about that more later. But what this principle really tells us is that no 2 electrons in any one atom can have the same set of all 4 quantum numbers, right? So like for instance, if this one, and this one are the same, then your spin quantum numbers have to be different. Does that make sense? So if you have 3 numbers that are all the same, that's fine, but then the MS value has to be different. You can't have 2 electrons with all the same 4 quantum numbers. It's just not possible. All right. So this is an important rule. We'll be talking about this a lot in the next lecture video as well, and it's something that we apply pretty often. All right, so let's do some problems. The first problem is, what are the possible set of quantum numbers for an electron in an f orbital at energy level 5? Okay, so if we're going to do this, there's actually many different solutions to this problem. However, there's 2 quantum numbers that have to be set in stone. And the first one is the n value. Since I know that the energy level is 5, and I know my principal quantum number is equal to the energy level, then my n value has to be equal to 5. That's the first one. The second one is L. Because we know we're in an f orbital, right? We know L, our angular momentum quantum number, dictates what type of orbital we're in and has specific values for each type of orbital. The L value for an f orbital is L of 3. So these are the first 2 numbers in our possible set of all 4 quantum numbers that an electron must absolutely have if it's in an energy level 5 orbital, and specifically that orbital is an f orbital. The rest of these values can be any one of multiple options, right? It says a possible set, so one set of quantum numbers. So we want one ml value and one ms value as our last 2 values here. But ml, if we think about it for L of 3, can be 3, 2, 1, 0, -1, or -3. So if you pick any one of these values, any one of these, sorry, I missed one, -2, -3, any one of these 7 values, you could put right there. So I'm just going to pick -2. It could have been 3, 2, 1, 0, -1, -2, -3. Any one would be acceptable. Our MS value is always going to be either equal to -1/2 or +1/2. And in most cases, it doesn't matter which one we choose. I'm just going to put -1/2 just for fun. And so this would be a possible set. Technically, it could be any one of those ML values, or either one of the MS values would be a possible set of quantum numbers for this electron. Okay, let's talk about an example problem where it does matter whether we put a -1/2 or a +1/2 for MS. What are the quantum numbers for an electron that is paired? Now, paired means something very specific. To an electron with the following quantum numbers. So we have an electron in exactly the same orbital as this other electron. That's what it means to be paired. It means the same electrons are hanging out in one orbital. And due to the Pauli exclusion principle that we learned about in the last slide, we know that no 2 electrons can have the same set of all 4 quantum numbers. What this means is, since they're in the same orbital, that means they have to be in the same energy level. Since they're in the same orbital, they need to be in the same type of orbital, L of 2. And since ml is exactly the specific orbital that they're in, the ml value still has to be -1. Notice I've just copied all 3 of these first values that I was given for the electron that the electron is paired to. Now ms is where we have to be different. We can't have all 4 numbers be the same. Since it's paired to this electron, it has to have the opposite spin. And since the other electron has a positive 1/2, this one has to have a negative 1/2. Okay, so this brings us to some other questions that we could be asked. How many orbitals are present at n of 4, right? Well, orbitals, how do we find orbitals? We need to know how many ml values there are. ml tells us how many orbitals are present for any type of orbital at any energy level. Now, I know n of 4 means what L values? It means that L could be 0, 1, 2, or 3. And this means I need to count how many ml values I have for each one of these L values. So what are my ml values? ml for L of 0 would be, my ml would be 0. ml for L of 1 would be 1, 0, and -1. ml for L of 2 would be 2, 1, 0, -1, and -2. And finally, ml for L of 3 would be equal to 3, 2, 1, 0, -1, -2, and -3. So if we count all of these values, right, I have 1 ml here, that's 1 orbital. I have 3 here, that's a total of 4, because 1 plus 3 is 4. I have a total of 5 ml values here, that gives me 9. And finally, I have 7 here, that 9 plus 7 would be 16 orbitals present. Now, that's how many orbitals we have at energy level 4. Now, if we wanted to do this a slightly less arduous way, there is an equation for this. Number of orbitals is equal to n squared. So notice that our n value is 4. What's 4 squared? That's 16. Hey, that's what we got over here. This is the theoretical reasoning why this equation works. All right. Now, how do we calculate maximum number of electrons? Well, in the previous slide, we learned that the maximum number of electrons any orbital can hold is 2 electrons. So if I wanted to know how many electrons I can hold at n equals 6 at a max, then I need to find out how many orbitals there are at n equals 6 and multiply that by 2 because each of those orbitals can hold 2 electrons max, right? And since we know number of orbitals is equal to n squared, 6 squared, 36. And since each one of those 36 orbitals can hold 2 electrons, I'm going to multiply by 2. This will give me 72 electrons can be held at energy level 6. All right, so those are some problems involving quantum numbers. As always, if you have any questions at all, please don't hesitate to email me, come to office hours, or email me and we can schedule a Zoom meeting one-on-one. Always happy to help you guys.